Okay, Math 2265. We're doing hypothesis testing some more, and we're in the OpenStax new book, and in chapter 9, 9.1, in just a moment. And we've covered some of this in the DeVore book too, and they actually were surprisingly clear on this. As you know, the OpenStax is more of a workbook and does have some good material in it, but it's on the other end of the spectrum from the DeVore book. So we'll try to get the best of both worlds, I suppose. We want to differentiate between type 1 and type 2 errors. We want to describe hypothesis testing in general. We want to conduct and interpret hypothesis testing for a single population mean with a standard deviation either known or unknown, known as Z, unknown as T, similar to confidence intervals, and also for the proportion, which we'll be using Z for that. So one job of a statistician is to make inferences about populations based on the samples taken, because you just can't get censuses all the time. In fact, they're extremely rare. Um, and yes, you could do confidence intervals, and in some ways, a two-tail confidence interval, as we said before, is just the same as hypothesis testing. Trouble is, we don't have two-tail hypothesis tests, is what I meant to say, all the time. They're very often one-tail tests, either towards the left or towards the right, or perhaps two tails when they do overlap nicely with the confidence intervals. But we're not going to overly depend on that. I will bring it up here and there. Car dealer might advertise this new small truck gets 35 miles per gallon on average. Maybe it does, maybe it doesn't. And then another tutoring center says that their method of tutoring helps 90% of its students get an A or a B. Maybe it does, maybe it doesn't. A company says its women managers earn an average of $60,000 per year. None of these have directions involved, so they're both then defined to be two-tailed tests, and that either they're true or they're false. And when they're false, they could be lower or higher. Often, though, you'll see it going in one direction, and we'll only stay in that direction, such as greater than. We'll ignore the lesser than portion. Okay, hypothesis test involves collecting data from a sample, evaluating the data. This is a bit of a review of what we talked about before. Then they make a decision as to whether or not there's sufficient evidence to reject the null hypothesis. Remember, it's a null hypothesis world. Either it's rejected or you choose not to reject it. You could say you prefer it, but you're not exactly rejecting it. So that's the formal situation. You either reject HO, which means you like HA a little better, but you have to say it as you reject HO, or you choose not to reject HO, which means you do like HO, but you're not exactly accepting it. Preferring it might be okay, I guess, but the official way is to not reject the null. Okay, anyway, we will talk about 9.1 and 9.2 today, as time allows. And we have the two contradictory hypotheses. Yes, we talked about this before. We set them up. The HO, the null hypothesis, always has the equal sign. In fact, that's all I care to see is the equal sign. If you'd like to put something else in there, in some cases, that's your business. But why make it hard on yourself? Why not just start off with mu equals 3 or whatever? You don't have to worry about less than or equal to 3. But at the bare minimum, you have to have some kind of equality in HO every time. Collect sample data. We'll give you the summary statistics. Determine the correct distribution. It's going to be Z or T. So it could be other things, but those are what we'll focus on. Analyze sample data by performing calculations. That lets you figure out whether to reject or decline to reject the null hypothesis. And then, sometimes it's tough for people, make a decision and write a meaningful conclusion. Don't have to write a term paper, as I know somebody over at Chaffey College requires a term paper to get an A in a class such as this. I'm not doing that, but the least we can do is ask you to summarize it in a short sentence as to what happened. And I'll take almost anything, assuming that's correct. But if you leave it blank, then that's probably not so good. Okay, so let's move on and get to the next section. So here we are in 9.1. I believe this is 9.1. Yes, it does not really show it very well, but this is 9.1. It's really hard to tell because they don't show the headings very well in this book, the online version. So we have the two hypotheses. Of course, you have the null hypothesis and the alternative hypothesis. We've already talked about this. Of course, they cannot be saying the same thing. They have to be completely contradictory to each other. That's another way to say it. Both books are saying the same thing. I never really thought of it that way, but they cannot have any overlap at all. So that does make some sense, but so many books don't say it quite that way. You do have to make a decision. It's like you're the umpire, you're the referee. You get to make the call based on the available data. And so you reject HO if the sample information favors HA, alternative hypothesis, or do not reject HO if the sample is insufficient to reject the null hypothesis, meaning that then you would have to prefer HO. So HO will always have the equal sign. That's the way I treat it. I will not even pay any attention to these. That's your business. You're sometimes walking on thin ice if you go in that direction. So I'm just forewarning you now, you don't need to do that. The book does have, although the book does lean this way, which is like the old-fashioned way of doing it, in my opinion, but they do at least one time say that yes, equals is always okay with HO. So I will definitely highlight that part. Now HA for a two-tailed test will simply be not equal. And if you don't see any direction given, that means it is meant to be a two-tailed not equal situation. And or if it's a right-tailed test, it'll point in the right direction. You see the arrow pointing to the right. If it's a left-tailed test, it'll point in the left direction. And yeah, so you could say less than, or it's just saying the same thing twice. HO always has an equal sign in it. HA never has an equal sign in it. That's how you can remember the two. Let's get rid of that little announcement there. And let's see, how about this example here? This is just lots of brief examples. And I will say it the way I prefer to see it. And it says no more than 30% of the registered voters in Santa Clara County voted in the primary election. In other words, yes, you could say P is less than or equal to 30, but P equals 30.30. They forgot the decimal point. That's their mistake, obvious mistake. P equals 0.30. But here's the key. HA really has more information in it. Sometimes that's all you need, especially in advanced work. More than 30% is P greater than 0.30. And then if you'd like to just say P equals 0.30, because we're just not focused on it being less than 30%, then equals is fine. That's what I would do. So I recommend you do the same, but there is no charge if you happen to use the old-fashioned notation. Don't say 30% though. That's considered to be something that I've just never seen done. It's just not considered to be correct. So 0.30, this is a typo in this book. Don't use percent, use 0.3. 0.3 is enough, or 0.30 if you like extra zeros, that's your business. So the try it, of course, this is an easy one. It's a trial conducted to test whether or not new medicine reduces cholesterol by 25%. So state the null and alternative hypotheses. I'm not able to write on the screen with QuickTime, unfortunately, so I'll just have to verbalize it for you. But HO is always equals, so P equals 0.25. And since it did not say greater or lesser than, then simply use P not equal to 0.25 for the alternative. So HO, P equals 0.25, HA colon P not equal to 0.25. And here's an easy one to see. We want to test whether the mean GPA is different from 2.0, and the null would be either equals 2.0 or as the alternative suggested, mu is not equal to 2.0. That could be a 1.0, it could be a 4.0. It did not have a direction. So it's really going both directions at the same time. And very important to see that. Sometimes the two-tailed tests are hard enough to see because you're so used to a direction, and then suddenly there's none. And sometimes people get flustered. It's like, where's the direction? And then they pick one and they're wrong. You got to pick the two-tailed situation where it's not equal to 2.0. I would consider that to be default position unless you see a greater than or lesser than somehow mentioned in the phrasing of the problem. So here we want to test whether the mean height of 8th graders is 66 inches. I didn't see greater than, I didn't see lesser than. That is simply an equal 66 and a not equal 66. And by the way, for these two-tailed tests, it's unanimous. All books say exactly the same thing. Equals on top, not equals on the bottom. There's no doubt at all about two-tailed tests because we're in universal accordance. Here, however, I disagree with it. This example lists mu greater than or equal to 5. Let's just say equals 5 and be done with it. Why not make it easy on yourself? I hope you will do that. If not, that's your business. But sometimes people will get it right for a while and they start to slip a bit and then suddenly they're not sure what's going on. So why not just pin it down? Make your HO always an equal and you will not have to worry about that. And you'll always get it right, by the way. But of course, this is a mean. It's not a proportion. Sometimes people don't know the difference, believe it or not. Not in a class like this, of course, but a mean and a proportion really are different. one could argue occasionally they're the same, but we'll never have a situation like that. So this one said less than 5 years. The alternative has all the information in it. All you really need is mu less than 5. And then the background thought is HO. Mu equals 5. Here's one that says fewer than 45 minutes. This is just in accordance with this last one. So mu would be less than 45. Let me start with HA first. HA is mu less than 45. And then let's just blanket it with an equals every single time for HO and make it easy on yourself. Students who make it easy on themselves very often are known for taking the correct shortcuts that get their finals done faster and do better on their tests. I can't say every single time, but predominantly that's the case. So that's why I say it. Here's a particular magazine who had an article on school standards, and it said that about half of all students take advanced placement tests on a third pass. But the same article said that 6.6% of U.S. students take the exam. So test of the percentage of U.S. students who take advanced placement exams is more than 6.6%. Now, they put in a lot of extra information here, but the real world does the same thing. Because I took a consulting class at UCR, that's one of the biggest things that impressed upon us, that the real world is full of extra junk that you have to sift out and simply not use, or perhaps hold as an alternative for next time. But right now, we don't care about the third, we don't care about the 4.4%. That just is not relevant. In fact, speaking of irrelevant, why not just say P equals 0.066? That's what I would do. But more importantly, the alternative says P is greater than 0.066. In the same way, I don't care about the leading zero. That's your choice if you want to use it. I just don't like it. I would just say P is greater than 0.66, 0.066, and P is equal to 0.066 in the null HO hypothesis. So here we have on the try it, this is just a whole list of practice. So you need to make sure you understand why these things go the way they are, whether you use the traditional way or the more streamlined method that most modern books use. On a state driver's test, about 40% pass on the first try. We want to test if more than, there's the direction, 40% pass on the first try. Go straight to HA, do it first. You don't have to do them in order. You just don't think that way. Think about the easiest one first. I think many of you are accustomed to that. So P is greater than 0.4. All you really need is 0.4. Then why not just say P equals 0.4? Because we don't really care about the less than situation. It's there, but we're interested in more than 40. We're interested in more like the 41 or the 49. Don't care about 20. That's hardly ever going to happen. If it did, there wouldn't be anything to test anyway for these one-tail tests. Okay, let's move on. And let's see what we have on this next one. See if we're still in 9.1. Okay, no, we're actually 9.2. This book is rather short compared to the other. Talk about two extreme books. And here's where I really wish I could write on the screen. I'm probably going to have to get my own personal Zoom meeting so I can actually do some writing. So this may be the last lecture without being able to write on the screen, because I know when I'm Zooming, I can actually write on the screen, which I find a lot more beneficial to everyone, including me. So in 9.2, outcomes in the type 1, type 2 error. Strangely, they do not give, well, here it is up on top. If I shrink it down, you can actually see it. There you are. So 9.2. But let's zoom in so you can actually read the page a little bit better. When you perform a hypothesis test, there are 4 possible outcomes depending on the actual truth or actual falseness of the null hypothesis HO and the decision whether to reject or not. Notice HA kind of stays out of it here because it's an HO world. The outcomes are summarized in the following table. Okay, yeah, the other book didn't really do this. This is where this book actually comes out ahead. So the actual truth or falseness is here in the columns. This is the true column, this is the false column, as if the golden tablets were handed out of the sky, out of the clouds, with the actual answer on it. That may not happen, but if it did, then we'd have a way of verifying things. But here's what we actually did. Either we rejected HO, which means we like HA better, or we didn't reject HO, which means we still like HO because we can't reject it. There are 4 different outcomes. 2 of them are correct, 2 of them are incorrect. And I'll also give you an analogy towards a jury trial about somebody who's being convicted of, possibly convicted of murder or jaywalking or something in between. Well, anyway, if HO is really true and you don't reject HO, similar to preferring HO, that is the correct outcome. That's wonderful. That's what we all strive for. Or, on the other hand, let's say HO is actually false, and you reject HO, which means the HO we think is false, and HO is actually false. That's also correct. So we have two correct situations, which is exactly what we're striving for. But these things are not perfect. We have to come up with the other possibilities. Turns out type 1 error takes up most of our attention here. For more advanced classes, especially found in the other book, you can get much more into type 2 error. I do not plan to cover type 2 errors very much, just in a rudimentary way. And yeah, the book is prepared to calculate all kinds of stuff involving type 2 errors, which would be fine. Given enough time, I could possibly do that. Or if all of you had had 2 years of calculus, perhaps that would be very helpful. But you're just starting calculus a lot of the time, and that may not be appropriate. Plus, it does take up a great deal of time. I'm not going to do that. Anyway, let's get back to where we are. So what is the type 1 error? Let's focus on that one. That's the most important error. You've rejected HO, but HO is really true. It's called a type 1 error. That is the second situation. We rejected HO, but HO is really true. It's an incorrect decision known as a type 1 error. Well, we should also give some play to the type 2 error. This time, you like HO. You don't reject it, but turns out later on you find maybe DNA testing comes along or something like that. And HO is really false. That's a different kind of error. It's a different kind of error called a type 2 error. That's the fourth situation here. The decision is to reject HO, but HO is false. Oh, I'm sorry, there's number 3. I misread it, sorry. Don't reject HO, you like HO, but HO was not really true. HA was really true. And that's an incorrect decision going the other direction. They're different errors. And that would also, well, here are the Greek symbols, lots of Greek symbols in this class, as you know. Alpha is the one we look at by far the most, probability of a type 1 error. It's the probability of what we just said, rejecting HO. HO is really true, and we focus on alpha. Beta is also available. That's the probability of liking HO, but HO was wrong. HA was true. They're rarely 0. In fact, I've never seen a case where they're exactly 0. They can be extremely small, but 0, that's unrealistic. And we'd like to minimize alpha and beta, and only one way to do that is to get, well, you could get lucky, but the foolproof way is to increase your n. Bring it up to 1,000, 10,000, 100,000, something like that. And then, of course, your alphas and your betas will be down pretty low. But most people can't get n's that large. So turns out that the power of the test, something we could focus on a little bit because it's a very easy calculation, simply 1 minus beta. And power seems to be almost self-explanatory. We would like a high power, as close to 1 as possible, as if that was going to happen. But increasing the sample size can, well, practically always increases the power of the test, in my experience, that is. Okay, I think what I'll do here, I wish I could write on this. Maybe I can do this on another lecture. If we have a jury trial, we could say that HO is actually true. In other words, that's where we say the person is innocent. Well, that's actually what happened. The actual event is innocence. Comes out of the sky, and the clouds say that, yes, that person was truly innocent, and over false, truly guilty. But we have to choose, not being privileged to that kind of information that's foolproof, definitely 100% accurate, such as golden tablets from the sky, which is silly, but anyway, it's in movies and all. Do not reject means we're saying that the person is not guilty and the person was actually innocent. That is correct. Okay, but if the person is guilty, which is over here, I'm trying to circle the guilty part, which is what we think is guilty, and if the person is really guilty, which is over here, that's also correct, but we have these types of errors which can also have other interpretations. I know I'm going a little on the fast side. This type 1 error says we think the person's guilty, but they're really innocent. That's the type of situation that movies are made of. This is an innocent but jail situation. They're going to jail, maybe the chair, but they're innocent. Type 1 error. Very, very sad. Very sad. All kinds of movies made before DNA came into play, and later on they found 50 years later the person was really innocent, and they were in prison for life and that kind of stuff. Horrible, horrible stuff. What about the type 2 error, though? This one we don't see quite as much, but here we think We're not going to reject the innocence. We think they're innocent or not guilty is a more precise way to say it, not guilty. But what's truly happening is they are really guilty. Oops, that's another kind of mistake. That's where they're guilty, but they're out free. They got out. Maybe on a technicality, I don't know. They're guilty but free. Generally speaking, it's considered to be paying more attention to the type 1 error in this situation. It's hard to put a ratio on this. We don't want anybody to be in jail when they're innocent. We don't like this one very much either, but it's not usually considered quite as serious to let a guilty person go free. We'd rather let a few of these guilty people out free versus letting anybody sit in jail who's innocent. Now, has this ever happened? I'm sure it has. I'm sure it continues to happen. But ideally, it would be kept to a bare minimum, very, very small. And perhaps at the expense of letting a few of these criminals out. Probably better to let a few criminals out than let anybody rot in jail when they didn't deserve it. But that could be considered a matter of opinion, I suppose. Okay, here's some other examples that they have put in. Suppose that HO, the null, is that Frank's rock climbing equipment is safe. So what about the type 1 error? Frank thinks his rock climbing equipment may not be safe. So we're rejecting the HO, even though HO really is true. So he's being overly cautious here. He thinks, oops, this might not be safe. But it turns out that if you really looked at it carefully, it really, really is safe. So that's something that would be annoying, but certainly not life-threatening. But let's take a look at that type 2. Frank thinks his rock climbing equipment is safe, but it's not. Maybe the rope is frayed or something, or termites got in it, or something weird like that that makes it not safe, but yet not especially easy to see. Okay, alpha goes with type 1. Alpha is A in Greek, beta is B in Greek. So they just go in the normal order. That's how to remember it. Type 1 is alpha, beta is type 2 error. So it's saying the same thing again, except they're putting the probability on it. And the greater consequence by far is type 2. Better to be safe than sorry, although it would be an error of sorts to skip your long-awaited vacation just because you're paranoid about your equipment. But that would be better than perhaps dying when you actually thought you had safety and you didn't, or severe injury, something like that. So we have some others. I guess I can run through what I came up with these. 9.6, HO, the blood cultures contain no traces of a pathogen. Type 1 error would be that we think that the patient, well, let's see, this is, here we go. Yeah, type 1, I wish I could write this in, but to summarize type 1 error, reject HO, but HO is true. That's saying that the blood culture contains pathogen, but we think they do. We think they contain the pathogen, but they don't. This is being overly cautious, perhaps. But type 2 is being perhaps reckless, just to put words on these things, similar to the last one. Type 2 says we prefer HO, but HO is really false. To put it in my words, which are a little simplistic, I like to avoid the double negatives, provided everybody understands that I'm speaking informally here and not as a lawyer might. Lawyers are rather exact and also sometimes difficult to understand. Well, anyway, here, this could be thought of as we think the blood culture has no pathogen, but they do. That could be a problem. That could be a problem. So here, type 2 is the more serious error. How about this one? The victim of an automobile accident is alive when he arrives at the emergency room of a hospital. That's HO. Type 1 error, though, says that we think the victim is dead, so we're rejecting HO when in fact the victim is alive. That doesn't sound good. What about the other type of error? We just flip the script, and here the emergency crew doesn't really know if the victim is alive. We think perhaps he is. We're going to give it to the fact we think they're alive, even though they're really dead. So this looks like the type 1 error is the most severe one. Because, try to resuscitate somebody who's already dead. It's a waste of time, but the person's already dead. Look at type 1, however. If we think the victim is dead, they're not going to treat him, even though they might be clinging to life. And that would be horrible. So this is why they generally err on the side of type 2 here. And alpha and beta are saying exactly the same thing as the type 1, type 2 error, except they're simply listing the probabilities involved. So I kind of treat these interchangeably. Alpha, beta are simply listing the probabilities of the type 1 and type 2 error. So it's better to define it. I don't need to define them both twice, which is sort of what's happening. What about this try it on 9.6? Looks like we had plenty of time for these. So HO, a patient is not sick. That's pretty simplistic. Which type of error has a greater consequence, type 1 or type 2? Okay, so to list this, type 1, we reverse it. We reject HO, so type 1 would say, we think the patient is sick. And it turns out HO is correct, and the patient is not sick. So this is like, once again, kind of the same theme again. We're, trying to help them out even though they're really not sick. It's like giving medicine to somebody who's well. Might have slight side effects, but I guess that's not so horrible. But you compare that to type 2, and that's different. We think the person is not sick. We think they're basically well, but they really are sick. So instead of getting the medicine they need, they're not getting it because we're overconfident in them. So the type 2, once again, right now, is a bigger problem. In this example here, it's a boy. Genetic labs claim to be able to increase the likelihood a pregnancy will result in a boy being born. So we test the claim with data, which we're not showing you, by the way. We'll show you the data another time. Suppose the null hypothesis HO has no effect on the gender outcome. Okay, so the lab really is just like flipping a coin. Nothing really is happening. Or if there's a small change, it's not significant enough to worry about or to take to the bank, so to speak. Here's the type 1 error. This results when a true null hypothesis is rejected. And in this context, we would state that we believe that the labs influence the gender outcome, but they really don't. That's alpha. That would be extremely disappointing. But let's compare that to potentially disappointing, that is. And so if you go into this situation, you want a boy. And so you would like some confidence that it would do that. Here's the type 2 error. This results when we fail to reject a false, that is, we kind of prefer the null hypothesis, but it really is false. Those are my words. So in the context, we state that the labs do not influence the gender outcome, but they really do. They really do. So the probability of this error occurring is denoted by beta. So this time, the greater consequence is the type 1 error, because then you got fooled by an organization that really isn't doing their job. Maybe you have like a 51 chance of getting a boy, or 52%. That really is not significantly more than normal. And the other one wouldn't be quite as bad. Just has no effect on it. Let's move on. I'm not going to do this one. I'll let you read that one. It's a rather longer problem. How about 9.8? Here, an experimental drug claims a cure rate of at least 75% for males with prostate cancer. Describe the errors. Type 1, the cancer believes that it's really less than 75%, so we're throwing HO out. So when it says at least, we just reverse it and go to less than 75, but it really is 75 or more. So we were falsely thinking that it's less than 75%, but it's not. Type 2. We believe that it has at least 75%, so we're going with it, but it turns out the HO is actually incorrect at this point, and the cure rate is really less than 75, so it's just like we're going the other direction each time. And they're saying the type 2 error has the most severe consequences. If the patient believes that the drug works at least 75% of the time, they would probably go for it. But then the cure rate is less than, and it could be quite a bit less than. It could be like 20% or something like that. And that would be potentially horrible, horrible. Now, if we're talking about 76 versus 74%, well, it wouldn't matter that much. But type 2 has the error as the much more possible way of having a more severe consequence. And that's why they're listing it as the worst one. Okay, so let's see about this one. Determine both the type 1 and type 2 errors. They give you 4 options here for the following scenario. 2 of them just don't do anything, and the other 2, one of them's 1 and one of them's 2. Assume a null hypothesis HO that states the percentage of adults with jobs is at least 88%. Identify the type 1 and type 2 errors. Well, type 1 rejects the null hypothesis. Okay, that looks like it'd be C or D. Let me read C. reject the null hypothesis of the percentage of adults who have jobs of at least 88%, but the percentage is actually at least 88%. And that, they said at least 88, and it is at least 88. That one does look like a type 1 error, and so that's the way that is. I may have to think about that a little bit. So we do have type 1 says reject HO. HO is true. So HO is true, and so we are rejecting it, and it is true, at least 80%. So C is the type 1 error. Then D is kind of going to nothingness because it starts off exactly the same, but then the result is actually less than. That's not even an error. So we reject it, and that's at least 88%. So they're saying it's not greater than 88, and it really is less than 88. That's not a mistake at all. So that means type 2 must be up here, and type 2 starts off by not rejecting the null, going with the null, in other words. And then we have to see that there's a contradiction at the end. So we say that it's at least 88%, and then it's actually less than 88%. That does flip the script. A is the type 2 error, C is the type 1 error, and B is nothing. Because if you're going with not rejecting the null hypothesis, that's at least 88%, and it's at least 80%, that's not even a mistake. That's not even an error. How about that? Let's see if I have enough room on my disk to get you a little bit of 9.3. Here it just talks about Z and T. They go very quickly through the first 3 sections, and even 9.4 isn't all that long. But 9.5 in this book has many examples, so I will discuss several examples and borrow from the other book as well as we go into the lectures coming up. Okay, so 9.3, distribution needed for hypothesis testing, which is up at the top there. Particular distributions for us right now will be Z, the normal distribution, or T, another version of the normal distribution. Standard deviation unknown, which is more typical in the real world, will demand the T distribution, but 2 out of the 3 times we'll actually be using Z, because they can just say to get started that we know the standard deviation. There is our sigma right there, and sometimes it is actually known. And then we could replace it with an S. If we don't know it, we can just do the same thing with the T distribution. And we still have mu, we still have this X bar for the sample mean. For the proportion, we'll always use Z. And yes, there's certain minimums that have to be followed, but we'll see if they pay that much attention to them right now. So we'll get to those. Here's the assumptions. When you perform a hypothesis test of a single population mean, here using the T distribution, there are some assumptions that have to be met. Your data should be a simple random sample that comes from a normally distributed population. We have a sample standard deviation to approximate the actual sigma from the population standard deviation. And by the way, if your size was really large, then you could, go for even non-normal situations. Well, maybe even more than 50 or so. So yeah, we're not going down that hole too much, I guess. Now here's the Z-test that often we start with. So we're using the normal distribution because we know what the standard deviation is. This is the known value, which they put at the end here. In reality, it's not known so often, but that's what I did to the Forest Service. I'll put it that way. And so very, very similar situations. It's just if you have your sigma, go ahead and use Z. That's your reward for knowing Z, for knowing sigma. And if you have S, which is more typical, please use T. And with technology,